はい、よろしくお願いいたします。Hello everyone. Today I'm going to present a paper on geometry-aware 4D video generation for robot manipulation. And this work is done by people from Stanford University and Toyota Research Institute. And they proposed a 4D video generation approach, which creates consistent multi-view videos for robot manipulation tasks. The main reason to why I chose to share this work is that while taking different approaches, I'm also working on the view invariance problem, where current action policy models have little to no understanding. Uh, uh, no really understanding. As a result, even slight shifts in camera viewpoint can significantly degrade policy performance. As a quick summary for the introduction, this work can be viewed in roughly two stages. This work proposed a 4D video generation model that predicts spatially temporal consistent RGBD sequence from novel views by enforcing cross-view, 3D point map alignment during training, and use the off-the-shelf 60OF tracker to extract robot trajectory from the videos, enabling manipulation policy that generalize to unseen viewpoints. I prepared two quick demos for the two stage I mentioned here, which are easier to understand intuitively. Here, the top row shows the ground truth of two novel camera viewpoints in RGBD on the left and right. The bottom row shows the generated 4D videos from these unseen viewpoints, also in RGBD format. As we can see at a glance, it's quite hard to tell the difference between the two. But if we look closely on the bottom left view, we can still see some artifacts on the target object box cover, as well as the slight blurriness on the gripper itself. Here is another demo for the second half for the downstream policy rollout from novel view. While comparing to a few different baselines, the point is that the proposed system is the most stable with highest success rate on the unseen view task execution. So the motivation is for robot manipulation. A robot must anticipate how scene will evolve. For example, how objects move, occlude each other, and respond to contact. And even for a single task in a single scene, a slightly different viewing angle can dramatically reduce the performance of an action policy. Traditional way of data collection on real-world robotic data is extremely costly and in many cases unrealistic. Alternatively, recent video generation models offer a way to learn its intuitive physics to generate plausible future and plan against them, often at much cheaper cost. Why is it difficult to leverage existing video generation models for robotics? There are a few reasons. Pixel-based video models such as Stable Video Diffusion model handles motion well, but lack 3D structure, causing flickering, deformation, or object disappearance. 3D-aware methods enforce geometry, but are limited to simple static single object scenes. So the goal for this work is to maintain temporal coherence and 3D consistency across viewpoints for dynamic manipulation scenes. By temporal coherence, it means to generate smooth and causally consistent motion over time. By 3D consistency, it means by preserving geometry and spatial correspondence across viewpoints. So here is the full pipeline overview. In the first half, having a trained latent video diffusion model from two RGBD viewpoints to predict future frames. Subsequently, using off-the-shelf 6DOF pose tracker to track the end effector pose in the generated video. Last, translate its tracked pose from the viewpoints to robot actions. And let us look into the first part. So starting from the two viewpoints RGBD images on the left, the 4D video model generates both RGBD and a shared point map on the right. For the point map generation process, the author adapts a pixel-based 3D coordinate map method called Docswell. The trick is to train the diffusion model to jointly predict the point map. For example, a point map from the reference view VN expressed in VN's own frame, and from the other input, the point map from the second view VM is re-expressed in VN's view. So they are trying to generate the same shared point map view, despite of the input point viewpoint is different. And once trained, the model can take RGBD observation from normal view and directly predict point maps in the reference frame, and no camera poses needed at test time. And that's where the author claims for the generalization across the viewpoints in this work. And the backbone is a stable video diffusion model. They use RGB VAE from the original work, which is frozen, and encodes each RGB frame to a latent. And additionally, they added a point map VAE, which is a separate VAE initialized also from the SVD's pre-trained data, pre-trained weights, and fine-tune on the point map data. The two latents are concatenated along the channel axis, giving the unit a unified RGB plus point map latent. They reuse SVD's pre-trained weights, so the model inherits motion prior without training from scratch. And on the decoder side, this is where they did things a little differently. Two units decoder with identical architecture are used by using independent weights. The VAE decoder turns the denoise latent back into RGB frames, one per view. On the other hand, decoder block of the reprojection view VM's branch is added with a cross attention layer from the reference view VN. Sorry, the VN and VM is a little bit confusing to pronounce here, maybe. Yeah, but as the graph shown here, we set the query from the reprojection view VM on the right, top right, and the key value pairs are from the latent of the reference view VN. So this is the main trick that channels through the geometry information flow from the reference branch into the normal view branch. And there are three training objectives plus one trick that they apply for training this video model. The first two are the RGB diffusion loss on the both views, which are the standard SVD objectives. And the third one is 3D diffusion loss applied to both native point map and the projected point map. And the one trick they apply is the indicator function, and where the indicator function expressed here as WG of T dash equal 1, which means that if a pixel value on a spatial wet map is 1 or 0, which they always set to 1, they add this indicator function to effectively doubling the contribution loss of the term at the gripper region. Because going back previously, when they extract the 60OF and affect the post tracking, the gripper reconstruction and the consistency is extremely important for the downstream task success rate. So that's why they added this trick to enforce, in this case, doubling down on the penalty of the gripper region reconstruction. And for the evaluation or for the implementation, they use SAM2 segmentation model for the real world data and just simply using the segmentation mask for the simulation. And at the inference steps, they first mask the gripper in the first frame with SAM2, and then they run foundation pulse, which is the off-the-shelf 60-OF pulse tracker, and generate RGBD sequence. And in order to use foundation pulse, we needed to provide a camera intrinsic and the gripper scat model as an input for the highest accuracy. And in return, it outputs SE3 gripper pulse per frame plus confidence of the prediction. And this will be run on both views to keep the result higher confidence. And once we get the SE3 coordinates, we transform it into a global frame using reference views known extrinsic. And on the gripper open-close detection, they simply use the projected two finger point clouds, measure the distance between the centroids with a threshold. And lastly, execute this in an open loop manner and replan on the next observation. The key points are the first, there is no policy trained. The policy itself is a video model plus a post tracker. Second, generalization comes from the video model's view invariance, not from imitation learned features like the more commonly see VOA or VAM, etc., etc. And here is the experimental setup. They mainly did more evaluation and simulation and kind of show that the video generation can be applied in real world. In this case, they have 3 top table tasks in simulation, 25 demos across 16 camera poses, 12 used in train, 4 used in test. And the camera position are sampled from the half-sphere shell, like the figure shown below. And on the right, for the real world, similarly, they have 4 tasks, but because it's real world, they only have 20 teleoperated demos for each, and only have 2 cameras set up at different angles. And yes. And quickly moving on to the result, first on the quantitative evaluation of the quality of the generated videos. So here are a few metrics, MIOU, which is probably the most important part. The MIOU measures the reprojected gripper mask reconstructions. So essentially, the higher the score in the red highlighted box here is, the better the model will be able to track the end effector pose, and in turn subsequently can execute accurate manipulation maneuver. And if we look across the table of the rest of the results on RGB and depth generation, the proposed method wins essentially on every matrix. And here are some qualitative results. We can see from top rows, ground truth, At a glance again, the proposed method seems almost identical to the ground truth, regardless of the RGB view, depth view, or the consistency of the n factor segmentation or detection. While if we look at some of other baseline, we can see quite a lot of inconsistency and noisy in detail as we usually expect in the video generation model. For example, the red highlighted box shows that the gripper shown to be on a lower position for a camera, but on the right camera, it shows the gripper already moving on to a higher position in the frame. And here's the result of a policy rollout and its success rate on the normal view in simulation. As we can see under unseen view, the compare baseline almost seem to be set up to fail. It's very low success rate compared to the proposed one. And on the other hand, author did address each baseline's model's shortcoming. For example, for the imitate, there is no depth and no geometric consistency, thus the view inconsistent video was generated, so the bad pose causes the low success rate. And similarly for diffusion policy, the implicit feature cannot bridge viewpoints. And despite multi-view training, multi-view data is used in training. And DP3, it does involve depth data. It helps on grasping on some of the tasks, but still fails in nitty-gritty detail of the manipulation maneuver. So in conclusion, what the author is claiming is that the explicit geometric supervision plus off-the-shelf pose track on the RGBD results, the best action signal stays accurate across views. The author also shows some computation trade-off. Even though I'm not sure how relevant these can be with this much gap in the end result success rate. But this proposed method costs 2 times inference time over SVD, for example, to predict the point maps, and 15 times over for the Gaussians. However, for the Gaussians, collapse on normal views in real world setting, if we go back to the qualitative results, and we can see on the bottom row, we have multitask real world data sets, and the evaluation for 4D Gaussian is almost towards 0. So in short, the author claims that the cost of inference of the computation buys generalization very well. And this will be last slide. In summary, here are some of the limitation of this work. First, on the data requirements, which in this work, it needs multi-view RGBD camera data with varying camera poses. This is easy in scene, but very painful in real-world setting. Second, inference latency of 30 seconds for 10 frames blocks. Sorry, this should supposed to be an open loop reactivity. So this deployment is executed in an open loop manner. So due to this inference latency, it's very difficult to do, for example, dynamics tasks, or if suddenly there is a disturbances happened. Third, a single task model. Each task is trained separately. There is no joint model across the task. Lastly, I found out that there are no real-world robot policy rule evaluation. And suppose there are some reasons to this. The author didn't explicitly address this outright. But when I think about looking at the limitation sections, the limitation listed here is probably the reason why they didn't do the real world robotic rollout. And on the open review rebuttal, I saw the main claim is that the policy results are in simulation, but underlying video model has been demonstrated to train and be effective in real world data. So I think their claims stops there. And since this is ICAOI is not strictly a robotic focused conference, I thought this is probably enough within their scope as well. And the key takeaway is that the point map alignment is a really strong inductive bias for the video models. And second, decoupling perception from policy works with zero policy learning to achieve viewpoint generalization is actually quite impressive, even though this seemed to be quite a heuristic approach. But with zero training cost, and I think it still has its potentials. And the afterthought from myself is that this setup trades between cost and generalization can be worth paying in some real world cases, especially even though the main trend in the research field are looking for generalist robot policies, which is a robot policy that can do everything, even cross embodiment. But in reality, many of the repetitive tasks that's yet being automated in industry is not that dynamic, but still challenging to deploy. So in some future direction, I kind of have I kind of looking forward in this direction with a faster generator at the diffusion generation step, and maybe hierarchical inference to decouple the policy execution and the actual trajectory generation. And also, since it is single task, we can do multitask. And lastly, robotic role model with explicit geometric, which is also the direction that I'm trying to tackle with my own current research. And this is all from my presentation.
Okay. Okay, thank you, Maripin-san, for the kind of presentation. So does anyone have comment or question for his presentation?
Can I ask a question?
Sure.
Yes.
What is this method necessary to predict depths? Was there any discussion about this point? I thought it was enough to predict only RGB as in typical world model.
Sorry. So the question is, does the video model predict depth?
Yeah.
Okay, so the video model itself does not predict depths. The depths are explicitly provided by the depth sensor. And in the paper, I think, or in the rebuttal, I kind of forgot. I think author did mention that in the future work, they could consider use depth anything like model to extract directly of the depth map from the RGB instead of using a depth sensor. But in this work, they do not predict depth. They predict point map.
But the depth point map is also kind of depth, I think.
Yes. If you consider 2D or 3D in that sense. Probably.
Yeah. Okay. Thank you.
Okay, any other question or comment? So my question is also related to the Sato-san's question. But could you please, for example, go to the page which shows a policy result, maybe comparing with a diffusion policy or some sort of that. Maybe page 17. And just several confirmation before my question. So if diffusion policy use multiple input in this case, right?
Yes, they provide the same multi-input.
But how about why don't you use a single view information? Is it still? My question might be related to the why each task cannot should use the multi-view information, or
Thank you. So why each task needs multi-view? I think it depends on the task setting. In
Yeah.
some cases, I think the author claims why the view invariance is needed is because there can be occlusion happenings, and to essentially dealing with normal view, stereo vision helps engaging spatial relationship. I think it will be difficult if only using single camera. This is my take. It's not anything that I recall from the paper. But yeah.
But the human do that. So only from single or from at least the two eye, so we can learn the spatial relation. So
Yes.
why do we need the multiple view or train or understand the spatial relation? So maybe my question is that is there any baseline about the single view input policy, diffusion policy? On the another question is that does it give some discussion about the data efficiency about the approach? Because in my understanding, this paper is kind of proposing the inductive bias about the point map matching is an efficient way to train the view invariant policy or any sort of the policy that can leverage the multiple view input. But in my opinion, so maybe it should be learned when training a massive training data. So I'm curious about whether there are any, cross point about that. For example, when the data size is increasing, single view policy might be effectively handle such a special relationship and therefore could provide a good success in the task, such as with some kind of occlusion also. My question is kind of there's some discussion about that point in the paper.
Yes, so there are kind of two parts that I can address your question. First, on the why two views are needed, and if human does not need, why robot need.
Yeah.
In this case, I think the assumption is that the the current state of our or the modern typical action policy on the same setting in the camera view, its performance drastically drops when there is a slight change in the camera pose. But human, we kind of looks stationary, but we kind of move around. I'm not sure if this is a right way. And this is kind of multi-view.
I also say it's kind of a circuit, I think. So in the eye is moving always. So maybe such a circuit might also help to learn such a view invariant representation thing.
Yes, so I think the challenge is that truly monocular, stationary, fixed point view trained policy is difficult to adapt, even with slightly changed viewpoint. So that's why two viewpoints, not just a stereo eye distance, but two viewpoints quite drastically different from pose, and leveraging inductive bias generated from the point map helps in normal view. In this setting, and the second half of how Sorry, the second half of the question
So
was
is that kind of a data efficiency?
yes.
So maybe my assumption is that when the data size is increasing, the single viewpoint policy might perform or might understand the special representation or special information well. So there is a kind of a cross point about, for example, the x-axis will be data size and y-axis will be the task accomplishment rate. Maybe there's a kind of a cross point even with single viewpoint policy and multiple viewpoint policy. And my question is that are there any discussion about such a data efficiency issue?
Yes, maybe not exactly to the point where Iwasa Sensei mentioned about data efficiency, but I just recall a part that was addressed in the paper describing the success rate in simulation. For example, in this one, the DP3, the diffusion policy in the middle, it says implicit feature can bridge viewpoints despite viewpoint multi-view training data was used. So I also believe in long train with a kind of scaling law. We have a bigger model, bigger data set. Essentially, we might be able to achieve view invariance, but then it comes down to how much of the distribution of, for example, this figure at the bottom, the camera view coverage is used in the data set. And for example, in the experiment that I'm personally doing with Droid dataset, the Droid dataset has, I remember, 70K thousand trajectory with over 1400 of camera poses, but still it's not perfect. So there, in my take, it feels like it doesn't feel quite efficient to really have even 1400 camera poses in Droid dataset cannot achieve a perfect view invariance capability. But in the long run, maybe with exponential growth of data and synthetic data and exponential growth model size and computation. But right now, it doesn't seem like quite a efficient approach to tackle view invariance problem.
Okay.
Yeah.
And any question from other audiences? Okay. And also, it's maybe just a comment or not out of scope of the paper. And I feel so the point map matching might be efficient way or elegant, one of the elegant way. But we can think many self-supervised tasks. For example, the feeding the another view from one VN from the VM or and any sort of there are any sort of self-supervised task, I think. And I'm curious about which task is actually efficient or which task help or kind of a comprehensive study about designing the definition or the self-supervised task given the multi-view or multi-view with depth for the information task and systematically evaluate which component or which type of the self-supervised task would help the policy training or spatial understanding. So in short, I think the paper could be the one of the example of the self-supervised task, and we can dig in more if we can formalize or if elegantly formalize the problem setup. So it's just a comment.
Thank you very much.